Step outside on Mars without a suit, and you have about 15 seconds. Not to suffocate, to watch your own saliva start boiling on your tongue. Every Mars documentary warns you about the thin air. Wear a spacesuit, otherwise you can't breathe. That part is true. But it is not what kills you first. Something faster happens before suffocation even finishes. It has an exact number, it has a name, it has a discoverer almost nobody knows. Mars's atmosphere sits near 1/10 of a precise threshold called the Armstrong limit. Below that line, exposed body fluids do not just fail you. They boil at your own normal body temperature with no heat involved at all. So is the real danger about breathing, or is the air pressure itself doing something to your body? Why would a planet with clouds and real dust storms be worse than deep space? Every other danger on Mars gets its own dramatic label. Radiation storms, dust devils the size of buildings, temperature swings past 100 degrees in a single day. The fastest, most certain killer barely gets a mention. It's treated as a footnote to wear a suit, not the headline it actually deserves. That saliva story is not fiction. A NASA test subject in 1965 reported this exact thing. It happened inside a vacuum chamber. It was the last thing he remembered. Zoom out for a second. All the way out, Mars looks almost gentle from orbit. Rust-colored deserts, thin white clouds drifting near the poles. Nothing about the view screams instant death. Now zoom back in. Down to a single square centimeter of exposed skin. That tiny patch of skin is where the entire story actually happens. Let's start with what Mars actually measures. Average surface pressure there is about 600 pascals. That's roughly 0.088 pounds per square inch. Earth's sea level pressure sits near 101325 pascals. Mars runs at around 0.6% of that. This number also shifts with the seasons. Carbon dioxide makes up 95.9% of the thin Martian air. It freezes onto the poles each winter. It sublimates back into the sky each summer, over and over, year after Martian year. Here's a comparison you can actually feel. That pressure matches Earth's air at about 45 kilometers up. That's nearly twice as high as Everest's summit. It sits well above where commercial jets cruise. Stand anywhere on Mars, and your body reacts like it's near the edge of space. Not metaphorically, physically. Lungs, eyes, skin, all of it would register the same thing, the exact same starvation for pressure that a stratospheric balloon pilot fears. One number explains everything else in this story. It's called the Armstrong limit. It's named after General Harry George Armstrong. The number itself is exact, 6.25 kilopascals. That is the precise pressure where water boils at 37 degrees Celsius, not 100 degrees. Just normal human body heat. Cross below that line, and boiling needs no stove, no fire, no added heat of any kind. General Armstrong wasn't chasing this number for curiosity's sake. He led aeromedical research for the U.S. Air Force during the early jet age. Pilots kept climbing higher, faster than medicine had ever tracked before. His research team needed one clean number that told engineers exactly where the danger began. 6.25 kilopascals became that number, and it has held for decades since. 6.25 kilopascals also lines up with something else entirely. It's almost exactly the pressure the U.S. standard atmosphere places near 19 kilometers up. Above that line, an ordinary oxygen mask stops mattering. The body needs total surrounding pressure, not just extra gas to inhale. Now put Mars beside that number. The planet's average pressure is 0.61 kilopascals. Even Olympus Mons sits at a crushed 0.072 kilopascals. That's the tallest point on the entire planet. Even Hellas Planitia only reaches 1.16 kilopascals. That's the deepest basin on Mars. Still below the limit. Nowhere on Mars holds enough pressure to keep your body's fluids liquid. No valley to hide in, no lowland shelter. Earth has mountains where the air runs thin, and sheltered lowlands where it doesn't. Mars offers no such escape. Its deepest basin still sits below the line that keeps human fluid liquid. Even that number moves throughout the Martian year. Pressure at a fixed spot on Mars can swing widely, roughly a quarter shift from summer to winter. That swing comes entirely from carbon dioxide freezing and thawing at the poles. But the swing never gets close to mattering for a human body. Winter low or summer high, both sides sit far under the Armstrong limit. Most popular Mars content frames this as a breathing problem. Not enough oxygen so you'd suffocate, the story usually goes. That framing isn't wrong, it's just badly incomplete. Suffocation and boiling body fluids begin at almost the same instant. Arguably, the pressure problem kills faster. No amount of supplemental oxygen fixes it. Not delivered by any method, not by any machine ever built. That gap in the popular explanation isn't malicious, it's just easier to say there's no air to breathe. Explaining vapor pressure curves on camera is harder, but easier isn't the same as accurate. This mechanism decides suit design, it decides mission timelines, it decides survival windows measured in seconds, not minutes. Think about your own kitchen for a second. Have you ever noticed water boils faster at a lower temperature, high up a mountain? That's not a coincidence. It's the exact same rule this whole story runs on. Why does pressure control boiling at all? Here's the physics made simple. At a fixed temperature, a liquid's boiling point depends on outside pressure. Lower that pressure enough, and the liquid boils at a lower temperature. This isn't exotic space physics. It's the same reason water boils faster on a mountaintop. It boils at a lower temperature there than at sea level. Your own body runs this exact test constantly, at 37 degrees Celsius. At that heat, water's own vapor pressure equals 6.3 kilopascals exactly. If ambient pressure ever drops to that number, water inside you starts to boil. No extra heat is required. Your own body warmth is already enough. The trigger is simply the outside pressure disappearing. That 6.3 kilopascal figure isn't a rough estimate. It's formally named the Armstrong limit, after the man who found it. On Earth, it matches an altitude near 19200 meters. That's roughly 63000 feet. It's the official cutoff in the U.S. Standard Atmosphere Model. Above that line, pilots need pressure suits or pressurized cabins. Ordinary oxygen masks stop being enough there. That 1965 story is real. It's documented first-person testimony. At NASA's Johnson Space Center, a test subject faced an accident. He was exposed to a near-vacuum environment. It happened during a routine chamber test. He didn't lose consciousness from any explosion. His last clear memory was small and strange. It was the saliva on his tongue. It was starting to boil. That chamber accident happened during a suit test, not some reckless stunt. Engineers were checking a prototype's seals when a hose failed. Pressure inside the chamber dropped toward near vacuum within seconds. The subject survived, and later described the whole event calmly. He said breathing became impossible almost instantly, but the boiling sensation on his tongue is the detail that stuck. Here's the part almost nobody explains well. This boiling effect is called Ebolism. It does not touch blood sealed inside your circulatory system. Skin and tissue keep that blood stable under pressure, but anything exposed to open air is different. Saliva, tears, the moist lining of your lungs, any mucosal surface at all, your lungs and eyes get hit almost immediately. Now apply that mechanism to Mars directly. Mars sits at roughly 1/10 of the Armstrong limit, not just barely below it like on Earth. Ebolism there starts faster and spreads through more exposed tissue at once. Moisture in the lungs and eyes starts vaporizing fast. At the same moment, oxygen pressure is already collapsing. Consciousness would not last very long at all. 2 clocks, both already running. Aviation medicine has a rough rule of thumb for this. Something like 20 seconds of useful consciousness once cabin pressure fails at extreme altitude. That number shifts a lot, depending on exact altitude and individual physiology. On Mars, both failure modes run together, not one after the other. There's a second separate problem stacked on top. Mars's atmosphere runs 95.9% carbon dioxide. Oxygen makes up only about 0.13% of it. Compare that to Earth's 20.9% share. Even without the pressure problem, that alone kills. Fatal hypoxia would hit within just a few minutes. 2 independent killers from 1 missing atmosphere. Confirmation of this threshold doesn't just come from planetary science, it comes from a completely separate field, military aviation. Pilots flying jets like the F-22 and F-35 climb past 18,000 meters. They wear specialized counter-pressure garments up there. There's exactly one reason for that gear. Losing cabin pressure at that height risks the same mechanism, the same ebolism that would strike an astronaut on Mars. Those garments squeeze the limbs and torso directly. Elastic bladders inflate the instant cabin pressure drops too low. The squeeze keeps tissue pressure high enough to hold blood and fluid in place. It buys precious seconds for a pilot to descend or eject. This isn't new territory for aviation either. Pilots of the U-2 spy plane faced this exact hazard first. That was back in the 1950s, flying near 21,000 meters. High-altitude reconnaissance forced engineers to solve Ebolism decades early, long before anyone designed a Mars suit. A fabric that protects a pilot above the limit on Earth obeys the same physics. Mars just applies it everywhere. That single fact reshapes how a Mars suit must work. No amount of oxygen compensates for pressure below the Armstrong limit. Suit designers can't just seal in some gas. They need a full mechanical solution for body pressure, built directly into the suit's own structure. NASA's Apollo Heritage EMU suits show how far that engineering went. Internally, they run at 25.5 kilopascals. That's 4 times higher than the Armstrong limit itself. It's roughly 42 times higher than Mars's outside pressure. Every layer of that suit answers to one number: 6 kilopascals. Nothing less will do. Compare that suit pressure to something familiar. A scuba diver at 10 meters underwater feels about double sea level pressure. NASA's EMU runs at roughly a quarter of sea level pressure instead, kept deliberately low for mobility. Even at that reduced number, it's still 42 times what Mars offers outside the fabric. There's a second, more elegant answer to this same problem. It comes from MIT, from a project led by Dava Newman. It's called the biosuit. Pressurized gas makes a suit rigid and balloon-like. Instead, the biosuit uses mechanical counterpressure. That pressure comes straight from the material's own elastic tension. The goal is flexibility across 1,000 spacewalks, the workload one single Mars mission may demand. Gas fights the wearer constantly. Every bend of an elbow pushes against trapped pressure, like wrestling a stubborn balloon with each step. That's exhausting even on Earth. Newman's mechanical approach sidesteps the fight entirely. It replaces trapped gas with woven tension that moves like a real body. This threshold even reaches beyond human survival. It's also why liquid water can't exist on Mars today. Below water's so-called triple-point pressure, ice behaves strangely. Warming ice doesn't melt into liquid at all. It sublimates straight from solid to vapor. The whole planet's climate history is quietly written in one pressure number. That reframing matters beyond pure curiosity. Any search for Martian life today has to work backward from this exact limit. Liquid water is the one ingredient every biologist agrees life needs. Orbital imagery shows what look like dried-up river channels and ancient shorelines. But images alone can't prove liquid water flowed recently or stayed liquid for long. The pressure math forbids stable liquid water today. Any search for Martian life has to work backward from this same limit, toward hidden places or a much older Mars entirely. Rovers like Curiosity and Perseverance have measured this directly, season after season, at ground level. Occasional frost and thin films of brine may form near dawn. None of it ever lasts. Within minutes of sunlight, that moisture is pulled straight into vapor. The same pressure deficit that would boil exposed fluid at the skin's surface. Let's make this simple enough to actually feel. Picture a pot boiling on a stove at sea level. It takes until 100 degrees Celsius to boil. Now carry that same pot up a very tall mountain. Thinner air there lets water boil at a lower temperature, maybe 70 degrees, even with the same stove heat. Push that logic to its absolute extreme. At one exact pressure, something else happens entirely. Water starts boiling at just 37 degrees. Body temperature, no stove involved at all. Stepping onto Mars without a suit does something similar. It's like being teleported to an altitude far higher than that mountaintop threshold. Every drop of exposed moisture starts trying to boil away, not because anything is heating it up, because the pressure holding it liquid has simply vanished. Boiling was never really about heat, it turns out. It's about the balance between a liquid's internal pressure and whatever surrounds it. Take away the surrounding half of that balance. The liquid escapes as vapor at whatever temperature it already happens to be. Your kitchen stove was never the real variable. The air pressure around the pot always was. So let's widen the view and gather the whole picture: a thin atmosphere, a precise number, a named limit. A documented human account, a separate field of engineering, quietly agreeing with all of it. Trace it back to the start. Pressure controls boiling point on any mountain or world. Your body runs right at the temperature where 6.3 kilopascals matters most. General Harry Armstrong named that exact line first. A NASA test subject felt it on his own tongue in 1965. Mars sits at 1/10 of that number, everywhere on its surface. Almost no oxygen sits layered on top either. Fighter pilots suit up against this identical threshold today. Engineers on Apollo suits fought the same 6 kilopascal wall. So does MIT's biosuit team decades later. Even Martian water history answers to this one number. Documentaries spend hours on radiation, they spend hours on dust storms, and on brutal Martian cold. But the detail that kills an unprotected human first is quieter than all of that. It's the same invisible rule behind a climber's oxygen tank, the same rule behind a fighter pilot's pressure suit, the same rule that changes how fast your pasta water boils at home. That rule never asked for attention, it just kept working, on every mountain and every cockpit, long before anyone pointed a camera at Mars. It has an exact number, it has a named discoverer, it has simply never gotten its own moment on screen. That drop of saliva is still sitting on an exposed tongue. In the thin Martian air, it's already starting to bubble, boiling away into a sky with nothing left to hold it down. That is the literal answer to a question every Mars documentary asks. Almost none of them ever actually explain it.